So we've got a program for you today that's out of this world. So we've got a program for you today that's out of this world. It's a Monday. It's late, right? Okay, I get it. I get it. So good afternoon, everyone, and it's a pleasure to welcome you to our inaugural Presidential Speaker Series, sponsored by Duke Energy. And let's give Duke Energy a hand for helping us today. This series is all about bringing together thought leaders and innovators who are shaping the industries that matter the most to our state, our nation, and our world. Everybody just come on in and find a seat. Through this series, we hope to spark fresh ideas, encourage meaningful discussions, and build bridges between academia, business, and government. We want this series to be a space where ideas intersect and collaborations take off. At Florida Poly, we are committed to a bold thinking approach, one that pushes boundaries and drives transformation and solutions. These series will be a key part of our efforts to inspire the next generation of STEM leaders, those who will lead in the charge of technology development and economic growth. And by bringing in top experts like we have today from different fields, we'll dive into very important conversations about challenges and opportunities that lie ahead. These discussions, I believe, will play a vital role in keeping us ahead of the curve, on the bleeding edge in our ever-changing world, and will help us connect the dots between education, research, and real-world impact. Now, looking ahead, I am thrilled to kick off this inaugural event and look forward to the exciting dialogue that's going to take place among these three experts today. Thank you for being a part of this initiative. Together, we're going to push the limits of knowledge and innovation. And I do want to say, this is not in my script today, but I do want to thank Dr. Abbott, one of our trustees, who came up with the idea for this panel. It's a very collaborative approach here, because not only do we have the opportunity to have these experts, but this is a part of a series that will begin exploring different ideas. It's also a part of our OPPE that we do as a part of our requirements for the BOG, for the Board of Governors, and for the state university system. So we have a collaboration going here, and it's really, really great to see. I also want to thank all of you for being here. We have a number of students, the most important people on our campus, and I want our students to stand up real quick and let us recognize you. These young people. So let me share with our UCF and FIT colleagues. This incoming class has a high school grade point average of 4.17. Their SAT scores average are 1313. The ACT score average is 30. That's in the 93rd percentile. These are the best and the brightest around, and we're very, very proud of them. Also, for those of you that came from the community, I know there are a number of you that are here today, and I'd like for you to stand up. If you just came from the community, there we go. Any other folks from our community? Yep. Thank you. Thank you for being here. I do want to extend a heartfelt thank you to Duke Energy for sponsoring the series and for their remarkable support of Florida Poly over the years. Duke Energy's commitment to education, sustainability, and the future of Florida is invaluable. And that dedication is embodied by the leaders who drive those efforts. It is my pleasure to introduce Laquita Gent, Vice President of Operations in Duke Energy's South Central Zone for Florida. In this role, Laquita oversees electrical distribution, thank God, across the key areas of Clearmont, Winter Garden, and Lake Wells, leading a team of over 350 employees and contractors. She ensures that efficient, cost-effective systems meet the needs of both the organization and the communities it serves. Laquita is a graduate in electrical engineering from Florida State University and has held leadership roles in distribution, reliability, and engineering at Duke Energy since 2006. She's also an active community leader serving on the board of directors for Polk County Pace Center for Girls and the past president of the Lakeland Alumna chapter of Delta Sigma Theta sorority. Please join me in welcoming Laquita Gent.
Good evening. Good evening. So this is a tough crowd I see, but I will say this. I am a graduate of Florida State, but when I graduated, this beautiful campus wasn't here, and this would have definitely changed my mind when I was making my decision. I just want to stand before you with before all of the Duke Energy employees, our over 2 million customers here in Florida. Now we struggle to get to that 2 million point, but we are there and we are growing. And I just want to say thank you for the opportunity to sponsor this event and to be a catalyst for the many opportunities that we have with our higher education and our community. We have several of the students that have interned that I've seen today on campus and that are now Duke Energy full-time employees. Let's give them a hand. At Duke Energy, we're always looking for innovative ways to think outside of the box as we transition to a cleaner energy future. What does that mean? We have an aggressive goal to make sure that we're being good stewards of our environment and to get rid of the emissions. And so this speaker series today is, we haven't tapped into going beyond, but we never know what's out there. And I'm always looking for opportunity. In Duke Energy, we're always looking for opportunity with learning. And this is what this is. It's a way for us to keep our minds fresh, but to be innovative in the way that we think, innovative in the way that we apply what we have learned in our communities that we serve. And so thank you so much for allowing us to be here and to represent Duke Energy. And I just feel a little bit inadequate because my test scores were not that of what were just read, but I'm very proud of our future. So thank you so much for having me today.
Dr. Abbott, I have to introduce you. Thank you, Laquita. I'm really pleased to introduce one of Florida Poly's own valued trustees. And today's moderator is Dr. Dorian Abbott. Dr. Abbott is a distinguished professor in the Department of Geophysical Sciences at the University of Chicago. He's accomplished over 100 peer-reviewed publications on topics from climate, paleoclimate, to planetary habitability, and exoplanets. Dr. Abbott is also known for his innovative teaching, having developed popular courses in Earth's atmosphere and global warming. Beyond his scientific work, Dr. Abbott brings a wealth of experience in faculty governance and university oversight, serving on several key committees at the University of Chicago and as an advisor for the University of Austin. He's been recognized for his commitment to academic freedom, receiving the Hero of Intellectual Freedom Award and the Courage Open Inquiry Award. He holds a bachelor's degree in physics and a master's and PhD in applied mathematics from Harvard. Dr. Abbott's expertise and dedication to open inquiry makes him an exceptional leader in both science and education. Please join me in welcoming our own trustee, Dr. Dorian Abbott.
So today, real pleasure of hearing from two of the most innovative scientists in this area, people who've had a real impact on the field. I've actually been lucky enough to author small papers. So our first speaker today is going to be Dr. Ramirez. He's an expert in climate modeling of terrestrial atmospheres, both in the solar system and in exoplanet context. And we're going to talk more about that word, exoplanet, extrasolar planet, planets, stars. He has a BS in aerospace engineering from Georgia Tech, PhD from Penn State in geoscience and astrobiology. After that, he worked as a research scientist at the Earth Life Science Institute in Tokyo, and he's been an assistant professor at the University of Central Florida since 2021. So what he's going to tell us about is an idea for terraforming climate of Mars, changing the climate of Mars to make it better for humans. And what's unique and interesting about that is his idea involves aerosols rather than just changing the gas composition. So that's kind of related to these ideas of solar geoengineering that you might have heard, Earth's climate, except those are supposed to cool the planet and this is supposed to warm it. Our second speaker is Dr. Chen. He's an expert in numerical modeling of terrestrial and gas exoplanets. He got his BS in physics from Boston University and his PhD in Earth planetary science and astrophysics from Northwestern. Then he was a NASA postdoctoral fellow. And since 2023, he's been an assistant professor at Florida Institute of Technology. And he's going to talk about the research he's done on exoplanet atmospheres and interiors, and then man-made magnetospheres on exoplanets that could reduce the stellar wind and stellar flares that can strip these atmospheres of these planets of their atmosphere. And so magnetospheres that can maintain the habitability. The speaker is going to talk for about 10 minutes. Then we're going to have a 30-minute panel discussion. I'll bring up a couple questions to get things going, and then we'd like to hear from all of you. So please save some questions. The first up is Dr. Ramirez.
Thank you. Thank you very much, Dr. Rapp. Thank you. Glad to be here. Pleasure to be giving this talk. Title is Anarons and Naval Settlement. So I work on a lot of things. I'm not going to talk about today, but I also work on exoplanets. Future students might be interested. But I have designed habitable definitions, space missions, and potentially elsewhere. And these habitable definitions are currently being used. If they haven't used by Kepler, have upcoming missions like they have. I'm also an advisor for space missions and events. Solar system, I'm really focused. I'm really interested also on all terrestrial, as long as they have a rocky soil. Most of my work is focused on Mars, and I'll also be talking about Mars today, specifically climate in the past. Right? I'm also interested in the other worlds. Today, something that I've been doing more recently is also looking at the present, more specifically how we as humans can modify it. So nature's modified Mars's climate in the past, and now I'm going to use basically the lessons that I've learned studying paleoclimate of Mars or the past climate of Mars to try to then use that knowledge to modify the current climate for our own purpose. So this is kind of what brings me to the topic today, and a little bit more on the present day climate. Mars. Well, Mars is, as we know, it's the fourth planet from the sun. Its atmospheric pressure, it's very different. It was different in the past. We think it was much thicker, but today it's about 67 millibars, and the mean surface temperature is 218 K. So this is more than 50 degrees below the freezing point. It's pretty cold and low pressure. And these values are much too low to support standing bodies of liquid water on the surface life. There's also no oxygen, at least no breathable oxygen that we use there, like on the Earth. And the planet's surface also sterilized, exposed to high UV radiation, galactic cosmic rays. So these are things and characteristics that make it not a very habitable planet today. Mars was different in the past. So mentioned it was potentially habitable. We see that in the geology, right? Presence of fluvial features, the field fans, deltas, lakes, all these geologic features that we see that are suggestive of a once more habitable planet, including ancient ocean shorelines. And these impressive valley networks that are basically analogs, Mars analogs of the Grand Canyon, are on large swaths of the surface, and they run for hundreds of kilometers. They're very big features that are suggestive that the planet used to be a much wetter place, a much warmer place, much hotter place. And so making Mars habitable again, like it was in the past, is one reason for terraforming colonizing Mars. But the other reason, there's a more philosophical reason, in my opinion, why we should terraform Mars. We don't want to end up like the dodo bird or the dinosaurs, right? And I think it's our prerogative. We want to preserve the beauty of our own civilization and our life in general, animals, plants, and everything that we have in this world. We're obligated to maximize our survival and expand out to space, just in case something happens. Like, you have a car, you have an insurance policy, right? You have insurance. Well, other planets in the solar system are also kind of like insurance policies. Now, this doesn't mean that human settling space includes our responsibility to the Earth. It's not like we send humans to Mars and like, oh, Earth's not important. No, these work in tandem. As the resources found in space, planetary settlements, there's a lot of resources on Mars, by the way. The asteroids that are also in the asteroid belt, we can mine them and so on and so forth. Also would help us here on Earth, people who decide to stay on Earth, alleviating the pressure off our own planet. So I see space as an extension of our own possibilities. Like, we don't want to cap and stay, keep our limits here. We should see space as the bold frontier to expand beyond our own limits here. Now, I just want to mention there's been other ideas to try to terraform Mars. So, for instance, magnetic shields that you could create this big magnetic shield to kind of reduce the radiation going to the planet, making it more habitable that way. Or you can have a space mirror that is properly positioned that you can warm the temperature quite a few degrees. And there's also just pollution, about CFCs and how those can actually warm these very volatile gases that break up the atmosphere, but they're very good greenhouse gases as well. But all of these methods that have been previously described to try to terraform Mars are too expensive and require transportation, construction of enormous amounts of material delivered from our planet. So they're not, in my view, feasible. How about, Elon Musk's idea to basically do heck out of Mars, right? Getting all the CO2 out of the surface and subsurface. Well, that's something that some of my colleagues looked into that a few years ago. Joukowsky and Edwards, they were to calculate, even if you were to mobilize all of the polar CO2 that's on the surface and what's also on the regolith that's been absorbed ice caps, you would only be able to provide about 1/10 the amount of CO2 pressure, 1/10 the stick of an atmosphere as we have here on Earth. And that's not enough. So we look at this chart here. The present day is the purple line. This is a plot of temperature and pressure. And 0.1 bars gets you to maybe 220 or a little bit over that K mean surface temperature, way below the freezing point, right? That doesn't get you very much, but where does it get to 273 K? Where it gets warm enough to get above the freezing point of water? Well, you can see the intersection point is really at 1 bar or so. So you need basically at least 1 bar of CO2 to get surface temperatures that are high enough that can support liquid water on the surface of Mars and make it happen. So unfortunately, there's nowhere near enough, 0.1 bar, if you were to try to terraform Mars today using the CO2 to try to warm it up. But there's another solution there that we came up with in recent years. Right, myself, Ansari, grad student, and some colleagues over at Northwestern, PMC also. This paper that came out actually earlier this year that I'm glad to talk about. So this was unique in that, unlike the other proposals that were really focused on trying to create or transport materials from the Earth, which would be politically expensive and they would fail in reality, we use this live off the land approach where we propose to manufacture these nanometer sized cylindrical shaped rods. So you can manufacture them directly from the Martians, iron and aluminum. They have to be at a certain size, but once launched into the atmosphere and allowing the circulation to transport these particles all across the planet, they can warm it up several tens of K, nearing the freezing point of water. So you have a very potent greenhouse effect from this nanorod mechanism. And it's actually more potent than all the other methods and a lot more efficient too, cheaper as well. I won't go into much detail on that, but you can read this paper, Ansari et al. 2024, and it goes into more detail on all those aspects. But depending on the model used, we used a couple different models. They all get that you get at least 30K of warming, up to about 50K or so. So even if the mean surface temperature doesn't get up to 273K, that's still warm enough that large swaths of the planet would be above the freezing point of water. So they would be able to support life as we know it. So you get large swaths of the planet warm with this, and the different color codes show the surface temperatures that you get, the resulting surface temperatures from these mechanisms. And so in conclusion, I just want to point out that it is our prerogative to ensure the survival of our species and Earth life in general by expanding out into space, starting settling Mars. I really do think, my team really thinks we can manufacture the nanorods from the iron-rich Martian soil, although we are looking at alternatives as well. I mean, this is not the whole story. We're looking at other ideas that we won't disclose today, but we are very interested in looking at different materials. But in this first initial test of concept, we wanted to show that the idea does work, but we can make it even better. Let's just say it that way. But in any case, by launching them into the atmosphere, you can have them disperse around the planet and give you a strong enough greenhouse effect that exceeds at least 30K and get large swaths of the planet above freezing and finally establish a human presence there. So at this point, what we're really interested in addition to revising this, continuing to revise this method, is hopefully interest more scientists and engineers to join us and make this dream realities. Contact us. And I will leave it there. I'd be glad to have a discussion later on, get to that point, but thank you very much.
Hello, can everyone hear me? I'd like to first thank Dr. Abbott and Dr. Stevenson for inviting me here. This is my first time being this far out west. I'm from Melbourne and the East Coast. And I also like to thank Dr. Ramirez for giving the preview of my subject of my talk, which is building a magnetosphere around a planet. And many of these concepts can actually be applied for planets in the solar system as well. I'd like to first admit that I am not a expert of planetary terraforming or planetary settlement, unlike my two colleagues here. My main subject of research is planetary evolution and habitability. However, I have worked on various subjects regarding planetary habitability in the long term. So I've thought of ways that you can help many of these exoplanets prolong their habitability range. So can you all see this, the text up there? Okay. Um, so we have discovered a large range of exoplanets, all the way from Earth-sized planets, sub-Earth-sized planets, to Jupiter-sized planets, and they're situated in this whole spectrum of stellar fluxes, possible stellar fluxes, and these different stellar fluxes largely determine their atmospheric composition, what condenses in the atmosphere, and what stays in gaseous form. And the idea of planetary habitability and colonization really is focused on the latter part, the latter category of planets, namely planets in the habitable zone. So we have discovered a whole range of different architectures, different types of planets around different host stars. And of particular interest are planets around M dwarfs because they're so small. Because they're so small and they're very common and they're much easier to detect because we rely on this technique where the planet transit in front of the host star. And when the host star is small, that makes the planet much easier to detect. One problem for planets around M dwarfs, and this is a problem for Mars and many of the outer solar system bodies, if we were when they go to these outer solar system bodies as well, is that they are vulnerable to EUV and X-ray photons, as well as charged particles from the star and from their respective star, from their sun and from their respective stars. So from the Kepler Space Telescope, we know that many of these stars show evidence of strong eruptive events. And these events are accompanied by photons and energetic particles that could be hazardous for the planetary surface. And this is even more exacerbated during the impulsive phase of these flaring events, where the X-ray and EUV photons can increase by 3 to 4 orders of magnitude compared to the quiet state, the quiescent states. So the issue with these high magnitude and frequent flares is that it could affect the composition of these planets and therefore harm potentially the surface life forms if there were any on these type of planets. And we have on the right-hand side is an observation of a large ozone depletion during a geomagnetic storm. So if you see an aurora borealis during these large geomagnetic storms, they have actually done a correlation between these large events and a decrease in the ozone abundance on Earth. So stellar eruptive events, and this is the goal of trying to build a magnetosphere, is to prevent some of these negative effects of stellar flares. One of them is through the electromagnetic photons. So like I mentioned, it can increase by the orders magnitude of 3 during these strong impulsive phases, but also highly energetic particles can be accelerated by these flaring events. So these are the two problems exoplanet surfaces in terms of habitability are being faced. So these two strong, energetic, and eruptive events, because they are essentially sporadic. We cannot predict when they're going to happen. For Mars, this is less of a problem because the sun is more of a gentle giant right now. It doesn't really do the strong events. But for M dwarfs, they are very frequent and much more common. So for a planet that's highly magnetized, like the Earth, the solar wind and energetic particles are redirected and deflected to the poles. And what we get from on the surface, it just looks pretty. But the issue with tidally locked planets and planets around M dwarfs is that the charged particles and UV photons directly interact with the day side hemisphere. And that could be problematic for the not just for the atmosphere, but also for surface life. Now, analogously, for the solar system, we have Mars that it's very small, so the magnetic dynamo has largely ceased, so it cannot produce a strong magnetic field. Whereas Earth, we have a strong magnetosphere that can deflect most of these charged particles. From my own work, I found that by modeling the effects of stellar protons and stellar UV radiation on magnetized planets, showing here is the abundance of nitric oxide on magnetized planets. So we see that indeed during the flare peak, which is when the star is really active and spewing out lots of photons and protons and for the energetic particles, you can see a large increase in the NO abundance. However, for unmagnetized planets, you see a large increase in OH abundance on a day side. Now, why is OH problematic? Because OH is a strong ozone destroyer. It can remove loss of ozone during the strong flaring events, and that could be problematic for surface life. So we need some way to create a strong magnetic field for if we were to set it on exoplanets or any planet in the planetary body and in the outer solar system, we would need some way to create a magnetic field that prevents the surface from being bombarded by charged particles, as well as prevent the atmosphere, prevent atmospheric erosion during long periods of time over billions of years. This could completely erode the atmosphere, even if you have one, if you could create one in the first place. So even if we were to terraform the planet, these two problems may still persist. So this is a big issue. And in fact, if the Earth didn't have accreted magnetized material and didn't form a magnetic field, we probably wouldn't be here today, even if we had most of the factors of habitability in place. Okay, so how do we do this? There are a variety of methods to create an artificial magnetic field on an exoplanet. Now, I'm only going to talk about one, my favorite one, but there are quite a few. So the first one is to create a magnetic dynamo in the core. Now, this is probably the hardest because you have to drill down into the core somehow. And don't get any ideas from the movie. And then the next one is to create a continuous loop of currents. And the other one is to create a ring of discrete stations, place a bunch of stations around the planet, and that way you can also create a current. Last one is to create a plasma torus. That's also can create a current in the outer regions of the planet above the exosphere. Then these four ideas are presented by Banford et al. So this is not my work, but the work of my colleague, who is currently at NASA Goddard's Space Flight Center. So my favorite one is the creation of a large-scale space-based high current loop. And the advantage of this method is that it does not require a physical structure. It is superconducting and will not melt. It's less expensive, I would argue. And this is the method of using a plasma torus, the last method that I mentioned amongst the four, to create a ring current that can generate a global magnetic field, so a planetary scale magnetic field. So the major advantage of this approach is that it would not require a solid structure. In fact, this idea comes from our own planet because we have plasma structures that envelops the entire planet, and we can see that from satellite data. These things are called Van Allen belts or radiation belts. So in this case, for a planet, the radiation belt is created by a co-rotating ions and electrons that forms as a result of the interaction with the magnetic field. So nature is a little bit different. If we were to create a magnetic field, it would be the reverse. We would have to drive a current that creates in a plasma torus that creates the magnetic field. Now, how would you go about doing that? There are many ways. Well, one of them is that you can use take advantage of the nearby moons from Mars. You can take advantage of its 3 or 4 larger moons, and you can put out plasma that gets attracted by the planet, and it will eventually form a ring. So this is like what we observe for Earth. So this is a measurement of the plasma sphere and the ring current on Earth. So once a magnetic field has been set up and created, the question is, how stable can it be? Well, I think it might be very stable because our magnetosphere has been sustaining our plasma sphere and the ring current for a very long time. Once the magnetic field is created, the effects of stellar flares or solar flares should not directly reach the current loop. It would not erode the plasma or electrons that are already in there because it would be protected by the created magnetosphere. So, like I mentioned, radiation belt and plasma spheres are persistent features of Earth and potentially habitable exoplanets. So that one of the goals of JWST is to figure out whether if other planets have magnetic fields by detecting exo northern lights, so exo aurora borealis. And if we can detect it and features of radiation belt, we might be able to say these planets have magnetic fields or they don't, so we have to go create one. The other question is how persistent can it be? Well, actually, we think if we can, for every couple of years or so, provide it a source of ions or plasma, it can actually be very persistent because the input, and this is an example from Jupiter's moon, Io, which provides inputs of various heavy ions through its volcanic activity. And this feature around the moon has been there for a very long time, despite the fact that the volcanic activity is effectively sporadic. So we think this is not something we have to constantly put in, but rather maybe feed in the input maybe once a couple of years, so it's not overly expensive. So my key takeaway for my presentation is that many of the exoplanets are in a very severe environment because they're next to these highly active stars, and they may lack magnetic fields, but if we can create magnetospheres around them, we can potentially make them habitable. And these concepts can be applied potentially for Mars once we have the ideas, once we have the terraform ideas in place. We can think about how to protect Mars's atmosphere from the astrophysical perspective. Now, such magnetospheres will require direct evaporation of plasma particles from either a space station, depending on the geometry of the planet, depending on whether it has a moon. We can put an output of these plasmas on the moon as well. So these are some of the possibilities. So that's it for my talk, and thank you all very much for your attention. If you're interested in research or any sort of collaboration, feel free to contact me through my research website or email. Thank you all again for your attention.
So we're going to do a short panel for, I guess, we've got about 20 minutes. And we're hoping to have questions from all of you. I'm going to start off with just something to get things going. But if you have a question, we're going to organize a microphone so that everyone else can hear it. And so it gets on the recording. So the first thing I'd like to hear from you guys is if Dr. Ramirez could say the time scale that on Mars we might have to, wait in the future until we get a settlement, a permanent settlement, and then terraform the planet so the temperature is high enough, the surface pressure is high enough that you don't need a life support system. Your body won't pop, and so that we get oxygen on the planet, so you can just walk around without a gas mask. So I want to hear the time scale for terraforming and settling Mars, and then from Dr. Chen, the time scale in the future of when when humans might visit one of these exoplanets.
Thank you. Yeah, this is a very good question. Very, very hard one. Probably get different opinions depending on who you speak to. But in terms of the time scales, how long it would actually take to terraform Mars, it definitely depends on what method you use. I think what will happen in the short term, and I'm hoping in my lifetime, our lifetimes here, we're not actually going to terraform all at once. What I foresee happening is we're going to do a lot of experiments. There'll be localized bases that will be kind of sealed. There are ideas out in the literature to look at aerogels and things like that by some my colleagues of mine as well to maybe get a localized greenhouse effect in the local area. That's probably where things will might start somewhere maybe, or in the nanorod's case, I hope we wouldn't just launch these nanorods out into the atmosphere and completely obscure the planet. It sounds dangerous. I mean, I would take it piecemeal and start looking at localized regions first and seeing if the concept works as well as we think it does. So that's going to take, um, a couple decades or something like that, right? To test the mechanism. And then once we become comfortable with it, I could see that within the next 100 years or so that we can try bolder experiments and maybe develop a much larger part of the planet. But during this time, what will happen is that um, there'll be a lot of science done. There'll be scientists doing things there and trying to understand the geology of Mars and its past and the potential for Mars to be a fully fledged terraform planet. But then, assuming all these tests go fine, and after the first couple decades, 100 years, then the next step is terraforming the planet, and that could take if this mechanism if it works. Then when we do launch it, these nanorods in there, then yeah, get temperatures close to the freezing point. That would also be relatively um, within a couple 100 years or something like that. But then to really then go to the next step of putting oxygen into the atmosphere, well, that would require first making sure that the soil is sufficiently rich in the materials that it needs and the elements that it needs. And so we need to fertilize the soil, and that would start locally. It would be a big project, right, to fertilize the soil, but we can do it. Mars soil is significantly richer than the lunar soil, but it's not as rich as terrestrial soil. So you have to first do that and do this on a grand scale. And then you can, put plants and start putting the oxygen levels. But I think that depending on the technological level, it can be very fast or very slow. So, if it's using our current methods, it can take millennia. But the problem with this kind of trying to extrapolate into the future how long this would take is that we ourselves are going to become a much more technologically advanced species, and so there will be methods to us that are just unimaginable to us today that we think, oh, from our technology it would take thousands of years or tens of thousands of years to terraform Mars, but we're going to have much better technology 100 years, 200 years, who knows, maybe in a fraction of a time, maybe we'll have a terraform Mars 200 years because there'll be all these crazy advances that beyond our wildest dreams that we'll get within the next 50 years or 100 years. So it really depends on, I think, the limiting factors, how but our rate of technological advancement. And if we become very technologically advanced very quickly, then those timescales of thousands of years or tens of thousands of years could be very well magnitude or a couple orders of magnitude less time than even that. That's really where the answer to the question is. It depends on the rate of our technological advancement.
That's a very long answer. Mine is really short. Um, the answer is probably never, but we do have ways to reach, for instance, Proxima Centauri system with something like nanoprobes within. If we do our traditional spaceship may take 10,000 to 50,000 years to get there, but with nanoprobes we can actually reduce the time to about 120 years with the breakthrough starshot technology. So that is something that has been considered to go to the nearest exoplanet. Proxima Centauri is the nearest system that has an exoplanet and the nearest star. So that's something that could be feasible. My hope is for Mars and for the outer moons of the solar system that could have water. For instance, Europa and Enceladus; those are good sites for potential terraforming as well. Um, but for exoplanets, they're going to be really challenging to even get to, unless we have things like you see in the movie Interstellar, the wormholes, right? I mean, that is a good way to reach some of these exoplanets. Most of them are actually thousands or hundreds light years away. So they're really challenging to get to.
Take questions.
The recording? Okay. Which one? Okay. Okay. So my general question for this is, strictly speaking, should the focus with all the the missions being prepared for Mars and all the research, should the focus necessarily be terraforming, considering from your answers how far away it is for us technologically? Would it not be better to instead focus on first preparing bases on these extraterrestrial planets and then doing all the proper research for terraformation on site rather than through simulation and uh, correlating with the behaviors of our Earth?
So thank you. Yeah, that's a very good question. And yeah, I basically I agree with you there that we don't. And my response alluded to this as well. That you don't want to terraform Mars right away. What you want to do in the very beginning is first, go do some science, learn more about the planet, test these ideas, and have it a marketplace, a competition between different terraforming ideas, which one's the best, and but you work on a localized scale. But yeah, I foresee even. I mean, I've written on this in Huffington Post, Scientific American, talking about these sort of things. How we need to do science at Mars first, but you would first start with a base there, some sort of local base, and you would need pressure suits and all that. But I think it is feasible with our current day technology. We do have the technology today to not even have to worry about terraforming, but put a base there. We know how to radiation shielding. We do have a very good handle on that at this point. Protection against radiation. We know how to get there. We know how long it takes. The technologies there, for instance, to convert the atmosphere into useful products like water and methane, rocket fuel things. We can actually produce them in situ on Mars using Sabatier reaction and similar reactions. These have been tested. These are things that have been known for centuries now. Like basic 19th century science that we know how to do very well on Mars. So yeah, there's a lot of stuff we can do right away how to terraform it. But yeah, you'd have to start.
I think it's a again very good point. I just have a one sentence answer for that is it seems like it's early to think about those questions now, but actually if you think of those questions now, it can help us here because people are asking a question of why go to space, why go to moon. Well, the technology to help us on that way is our advancements that we can apply here in our lives today. So I have many examples for that. but that's just the principle of it.
Thank you very much. Using the method that you spoke about of the nanorods, if it were to work and you're able to warm the climate of Mars to a desired temperature, would we have to continually pump these rods into the atmosphere to maintain that temperature, or just be open to they satiated at that temperature?
That's a great point. Thank you. So as far as the settling times, these particles will settle and have some idea, but I think we'll have a much better idea once we're there and so we can figure out, we'll test on a localized scale what the settling times are, and also what the fountaining rates need to be to sustain given concentration. So you more than likely will have to. These will settle. That's another thing. It's another issue is mechanism. One issue is mechanism, possible contamination, asbestos visiting, or some similar thing like that. That's a very valid critique mechanism. But there are ways we're thinking about it. Maybe these once they settle out, they dissolve, minimize the impact. So we're looking at ways to round this. So this is just that first paper is just a test study, pilot study that we will be building. That's the foundation, but we'll be building on this.
Terraforming is a really lofty goal. I believe what they were referring to maybe is building a dome on some of the planets at Mars as a starting point and going there. Um, Nobody mentioned domes. And the other thing I wanted to mention, not so much as a question, but has anyone thought about digging under the ground on Mars and using the energy from below the surface to heat things that may be down below the surface and working our way up?
Yeah. Yeah, good question. So again, I mean, I totally agree that we should not just go and straight away terraform Mars, but start small, whether base or characteristics of that base. You have a dome type of base. That's something that here's a need to figure out. You need to start slow. Run into any major problems, we start slow first. But we don't want to do something that we regret. Start local. As far as what's under the surface, certainly we should dig, and I think that my interest in the surface or the subsurface as a scientist, this big astrobiological question of whether they're second genesis, they're really the only ones in the universe or not, and if Mars is also very appealing in that sense. I don't know, but if there is life on Mars, it's probably fossilized, or might be microbial. But wouldn't be on the surface. You'd have to dig deeper to get to it. So that, from my perspective, is the interest that go subsurface. One major thing. But the second thing is that there's also in the Mars, the subsurface soil. There's frozen soil. There's a lot of water logging. So there's more towards the higher latitudes, and in addition to the caps, there's tons of, but there's also some near the equator, and we can certainly harvest that. And on that note, it's even more than that. Now pretty deep. So just a couple months ago, I want to say, from orbit, we detected evidence that there's water deep down, kilometers down on Mars. So Mars has a lot of subsurface that we can access, in addition to CO2. So on this question of terraforming, with current day technology, if we were to try to extract the CO2 that's on Mars, as I said in my talk, and try to terraform it, you'd only get a pressure about 1/10 we have on the Earth, would not be suffice to warm it up. Uh, but the thing is, there could be a much more CO2 subsurface. It just would be unfeasible and too expensive for us to access. But if we were to be technologically advanced enough, and there's a major breakthrough that we can actually access all that subsurface CO2 feasibly, then yeah, that would be a very good way to turn, just to use the CO2 inherent in it, as long as it exceeds 1 bar.
Couple little points. The first is you don't necessarily have to dig. There's caves on Mars you can put the settlements in, and they have sufficient thickness on top to act as a radiation shield. And then the other issue is Earth's geotherm involves an increase in temperature of about 40 Kelvin every kilometer you go down, but Mars is geologically dead. You don't get the same increase in temperature as you go down because there's not really much heat. So that doesn't help you as much. Okay, next question.
Hear me? Sure. I was just curious as to the science behind the nanorods actually surface. Yeah, so you said you're going to release them into the atmosphere. How do they actually increase the surface temperature?
That's a good question. Thank you. So how do the nanorods actually increase the surface temperature? Well, it's due to the fact that it's due to the radio transfer and wavelengths of light and getting them down to the exact dimensions that they're small enough that they actually have warming property. They can forward scatter the radiation to the surface is what they tend to do. Like the dust today on Mars, it can have a cooling effect, warming effect, but the particles are all sorts of different sizes. But for these manufactured nanorods, they will be a specific size that's specifically built for warming. So that's really the mechanism or the basic idea, and why these are warm. We would manufacture them so that they become warm.
So maybe a little bit different from the terraforming that we've been talking about, but how does that compare to kind of rotating habitats and why go for terraforming instead of rotating habitats or any other kind of, I guess, man-made habitats?
Oh, that's yeah. So as far as rotating habitats, or you're just saying official G in space, or just any. So, I mean, that's part of the plan. I mean, if you have, say, a mission that you send to Mars, microgravity is bad on the astronauts, so you want to have like a rotating habitat to create that artificial G, so that they can safely get to Mars and not have those adverse effects on their limbs. But major reason why putting, this thing, having a habitat in space or a base or something like that doesn't work, in my opinion, or not as appealing, is that planets have resources. Right? So you have lots of, Mars is actually rich in resources. You have water, you have CO2, you have iron, you have all these things. And you can extract CO2 from the atmosphere. You can all sorts of things that you couldn't do in just a base up in space. And not to mention that would be that you had a big base in space. How expensive would that be? So for me, it's about political will as well. Right? So I just don't see a lot of political will for that. And a major reason why initiatives to send humans to Mars keep failing is because the plans that are developed for them are so expensive. NASA's plans, like a $45 billion space mission in the 90s, died immediately politically. It was just too expensive. Sending these Battlestar Galactica ships to Mars that are just totally unfeasible. You don't want to do that. You want cheap. You want to live off the land cheap. something be light. And so on a light mission, that's why I'm also a big advocate of this live off the land approach, which is what this idea that we're doing does. And also Bob Zubrin, who's president of Mars Society, is a really big advocate of that. I'm a fan of, by the way. I think that's the way to go. You really reduce costs by just living off the land and using the resources of the planet rather than spending all this money and propellant to build something in space that's like billions and billions and billions of dollars. That's really so a few reasons why I think it's a much better way to just go to Mars.
And it's not a either or, it could be a both and. So Zubrin, who we just mentioned, wrote a book talking about a triangle trade, where in the asteroid belt you would have space stations like Bezos is envisioning. Then you would have Mars settlements like Musk is envisioning, and you could have miners in the asteroid belt on relatively unappealing stations who could then go down to Mars for entertainment, and you could also get resources from Mars directly and bring them to space stations and grow food there and things like that. So both things could be happening. But we're going to have a reception, so I hope everyone will join, and we're all going to be here to talk in person. But before we finish, we should thank a few people. So let's thank Dr. Stevenson, and we'll thank Dr. Ramirez and Dr. Chen for joining here and coming and sharing their knowledge. And let's thank Duke Energy for supporting this event. Thank you.